Hey, physics babies. So we are going to jump right on into our next lesson. My last videos have been a little long, so I'm going to try and make this short and sweet for you. This is Unit 6, Lesson 2, and we are starting to talk about some of the basics with waves. All right, so our objective is that by the end of the day today, you will be able to describe and label the parts of a wave, as well as calculate frequency, wavelength, and wave speed. So this is actually really cool. If you are not interested in a cool video, then I guess skip ahead about a minute and a half, but otherwise, let's check it out. All right, so this is all about pendulum waves. So as you can see, we've got a bunch of different pendulums all attached to one like central pivot point. The pendulums, however, all have a different length. What do we know about the length of a pendulum? Hopefully you remember that that impacts the period of it. So we're gonna watch, and it's really cool. They start to create these really cool patterns because each string length has a different period, so it takes a different amount of time for each of these little bobs to swing back and forth. But as we continue to watch, we're gonna keep seeing different patterns, and eventually, because a pendulum is a periodic motion, that means things repeat. If we watch long enough, we'll eventually get back to that same initial pattern that we saw. It's really cool. Their periodic nature means that like at certain points, things just kind of line up for a split second with it. And it's actually, I think it's really interesting. You might not care that much, but you know. And here we are. That same motion that we saw at the beginning has been repeated. Pretty cool, huh? That's it. I thought it was interesting. All right, so what exactly is a wave? A wave transfers energy through matter or space. So a wave is essentially a movement of energy. And they can look a lot of different ways, and we're going to talk about a few of those today. There are two main types of waves. The first one is a transverse wave, and this is where our waves move perpendicular to the transfer of energy. Please write that down. Transverse waves, they move perpendicular to the transfer of energy. Some examples of transverse waves include light waves, seismic waves. So that's like when our seismic plates move and we get earthquakes. It's a transverse wave. Water, like in the ocean. Radio waves, as well as gravitational waves are actually considered transverse. So that's kind of cool. A transverse wave, the particles are moving up and down. Whatever particles we're talking about, light particles, water particles, etc. They're moving up and down, but then the energy is moving to the side. If you think about a wave, you think about this kind of up and down, that's a transverse wave, okay? I will actually, yeah, I'll do that right now. I have a lovely, oh man, there we go. So I have a Slinky. If we were in class together, we'd get to do a fun lab. Unfortunately, we don't. But if we stretch it out, right, and make that up and down, we can see what a transverse wave looks like. It does that up and down motion, okay? Oops, that's not what I wanted, sorry. Okay. So there you go. Make sure you draw a little example of what a transverse wave looks like, because when we get to our next wave type, you don't want to confuse yourself. Okay, so our waves are moving perpendicular to the transfer of energy, right? The waves are moving up and down, but energy is moving to the side. We'll get into more specifics about what these different points are, but the high points we call crests. The crest of the wave is the very tippy top. The very bottom of the wave is called a trough. And then the distance from like the resting point in the middle to a crest or to a trough is called the amplitude. So our next wave type is a longitudinal wave. And in this case, our wave moves parallel to the transfer of energy. Parallel means in the same direction. So my particles are moving side to side, my energy is also moving side to side. An example of a longitudinal wave is sound. So sound moves like this. Let's look and see what it looks like on our slinky. If I can, here we go. So I'm gonna stretch it out again. A longitudinal wave will look like this. As you can see, I'm moving it and getting that energy going, and the rings move side to side. And if you look carefully, I know it's kind of hard to tell, but you can actually see how they kind of condense and then stretch back out. Pretty cool. Like I said, we would do this lab in class. So next year, if you have some time, feel free to stop by my room and we can mess around and have some fun with it. All right, moving forward. So longitudinal waves, again, parallel to the transfer of energy. Instead of having crests and troughs, we have compressions and rarefactions. So a compression, everything's getting closer together, all right? A rarefaction, everything is stretching out. It's kind of hard to show, I think it's hard to draw longitudinal waves, but if you try and draw like a slinky and you can kind of draw them really spread out and then draw them really tight together and then really spread out again, we can see the compressions and rarefactions a little bit better. Take a second, draw it, label it. Okay, here we go. So I've got a longitudinal wave at the top, a transverse wave at the bottom, and again, here you can kind of see, you know, our slinky deal, what that looked like. The crests of a transverse wave are like the compressions on a longitudinal wave, okay? So our compressions are, I don't want to say equal because like they're two different things, but they mean the same thing for our different waves, okay? I would take a second and write that down. All right, let's talk about wavelength. So wavelength, we use what's called lambda. It's that funny looking H thing that is right here. Oops, lambda right up there. When you are typing this into a Google form, I know we don't, it's difficult to find those Greek letters. Just use H and I will know you are talking about wavelength. That's fine. We measure wavelength in meters, all right? On a transverse wave, we measure it from crest to crest or from trough to trough. Essentially, it is the entire period of a wave. So we go through our wave. You could start your wavelength right here. We're going up, down, back up. That is one full wave, all right? Because once we keep going, my wave begins to repeat. We don't want to include any repetition in our wave. We just want one full wave. And that's why it's easiest to do it from one crest to the next or from one trough to the next. But you don't have to. We could take any single part in our wave. We could start, oops, let me mark it up. We could start right here. Oh, just kidding. We could start right here, follow my wave, and we're going to look for when will it start to repeat. Oh, right here. That is one wavelength. For a single wave, the wavelength will be consistent throughout the entire wave. Okay. On a longitudinal wave, we measure it from one compression to the next compression. Okay, that's the easiest way to do it. You could also measure it from one rarefaction to the next, but it's the same idea, right? You want one full section of wave without anything repeating. Okay, still lambda, you can use H. Write in your notes though that it is like it is a wonky looking H when you draw it, so it looks kind of like this. And please call it lambda, L-A-M-B-D-A. If you want to get technical and make sure you don't forget what that's called. All right, so practice. I've got a wave right here. I want you to take a second and label all the crests, label all the troughs, and label one wavelength. Pause me, do it. Okay, I'm gonna start talking through it. Points. Let me make this a different color. Blue. B and is a crest. I'm going to label it C for crest. F is a crest. These are the highest points of our wave. D is a trough. I'm going to label it T for trough because my handwriting on this is not very good. A single wavelength. We can go from B to F. This is one wavelength. There's no repetition, okay? I can go from A to E and say this is one wavelength. Or we could also go from C to G as one wavelength, okay? When you are picking from midpoints, you need 1, 2, 3 total, okay? So you've got the endpoints and then one midpoint in the middle of your wave to complete the wavelength. You could get real fancy schmancy and, you know, start talking about how from here to here is a wavelength. You don't necessarily need to, though. Honestly, the easiest points are to pick 2 crusts, to pick 2 troughs if you have 2, or to find 3 points in the middle, one after the next, and call them a wavelength, okay? If you have any questions about that, I know it might be a little weird, especially if we're talking about like the ACE as a wavelength. But a wavelength has 1 crest, 1 full crest, and 1 full trough within it. That's probably the best way to put it. 1 full crest and 1 full trough. If we look from point B to point C, I've got a half crest here, right? And we have another half crest here. 2 halves make a whole, and then here's our full trough. Hopefully that helped. If not, come talk to me and I will happily answer any of your questions, okay? Moving on. All right, so we've got some compressions, some rarefactions, and we need to find one wavelength. Where do you think the compressions are? Take a second. Where do you think the rarefactions are? Where do you think a wavelength is? Okay, I'm gonna pause it and that'll help. So, a compression is when we've got our wavelengths really tight together. So like right here, these are really tight together. That is a compression. Our waves are more spread out right here. That is a rarefaction. And again, to find a wavelength, you want no repetition. So I'm going to go through. I see my pattern starts to repeat from right here, right? I start here. Good, good, good. Nothing's changed. Nothing is repeating. It's all brand new. And then I get here and things start to repeat. So there's my one wavelength. You could have picked anywhere along here. It's fine, right? But go easy on yourself and pick the simplest points that you can find, okay? Moving forward. All right, let's talk about how many wavelengths we see in these pictures. Take a second and write them down. This is problem 1, problem 2, problem 3. Pause me, go for it. All right, talking about it. I hope that you said that A has a half of a wavelength. I'm not going to say a half. Lambda equals 1/2. Sorry, I'm going to just scratch that out. I'm going to say we've got 1/2. Why did I say 1/2? Remember, for our wave, we need 1 full crest and 1 full trough. This is not a full crest and full trough. This is one piece of rope that's moving up and down, up and down, up and down. What about number 2? I see 1 full wavelength, right? We've got from here, up 1 full crest, down 1 full trough. That makes it 1 full wavelength because this is 1 rope that is moving up and down, okay? Depending on the speed that you move it, we get different numbers of wavelengths. This one right here, let's count them. I've got 1 1/2. So I've got 1 full wavelength plus 1/2 of a wavelength being shown. I want you to take a second and think, which rope do you think is moving the fastest? If they're all the same initial length, which one do you think is moving the quickest? Okay, hopefully you picked one. The answer is this one is moving the fastest, and we're about to talk about why. Just kidding, we'll talk about why in a second. So, amplitude, A. We use meters as well to measure that. And an amplitude is a measurement of how much energy the wave has. On a transversal wave, we measure it from the normal, so the resting point, up to the very top of a crest, or down to the very, very bottom of a trough. It doesn't matter which one you use. Depending on the problem, one of these values might be easier for you to work with, so that's just, it's either value. Because the amplitude is the same throughout the wave. Just like the wavelength for a single wave will not change unless you change the wave. The amplitude throughout the entire wave will be the same. So if we look and draw, this is the same height as this, is the same height as this. This is the same value as this, and it goes as deep as this. Okay? Cool. On a longitudinal wave, our amplitude is the width of the compression. Simple as that. And again, the amplitude will not change throughout the wave if you keep the wave consistent. Okay. Next up is frequency. We use a small f for frequency. Please do not capitalize it because capital F is force. Our units are hertz, H-E-R-T-Z. We abbreviate it, capital H, lowercase z. Our frequency is how many times a wave passes by in 1 second. So we want to know the number of full wavelengths that pass by a certain spot per second. Okay. Just use hertz, honestly. That's the easiest thing to do. The conversion for hertz is 1/seconds. Okay. So to find frequency, we take the number 1 and we divide it by the period of our wave. Remember, the period of the wave is how long it takes for it to complete 1 full wavelength. Pretty straightforward. Okay, so this is a low frequency wave because for each second, because this wave is so large, it takes longer to go through 1 full rotation or 1 full wavelength. Because it takes longer to go through 1 full wavelength, we have less wave passing by a single spot per second. This is a medium frequency. It's in the middle in terms of its wavelength, right? We see a lot more happening. This is an example of a high frequency wavelength. As you can see, it has a very short wavelength, right? This is very small, so that means I have more waves passing by a single point per second. Draw these examples in your notes. It's important. It's good to know. All right, so wavelength, frequency, and wave speed. The greater our wavelength, the lower the frequency. Jot that down, maybe put a star next to it. So a large wave means a low frequency, where a small wavelength means a high frequency. And this is why I was saying that rope 3 was the fastest, right? It had a smaller wavelength. So that means it's moving faster up and down to get that motion happening. And it's got a higher frequency. Higher frequency means a faster wave. To calculate our wave speed, we're going to multiply the wavelength of our wave by its frequency. And that's how we get wave speed. We measure speed, the velocity, so we use meters per second. Wavelength is still lambda, and it's measured in meters. Frequency, F, hertz, or 1/second. Hertz is honestly probably the easiest if you can just memorize that. I know we don't typically like our units looking like this. But there you go. So we've got an example problem. We've got a wave with a frequency of 10 hertz and a wavelength of 1.5 meters. We want to know what the wave speed is. Well, here we go. I am given my frequency is 10 hertz. I am given my lambda is 1.5 meters. Okay, and I want the speed. I want V. So V equals lambda times frequency. So my velocity will equal 1.5 times 10. 1.5 times 10 is 15 meters per second. And there's our velocity. Pretty straightforward. If you think that sounds too easy, it's because it is that easy, I promise. Remember, virtual instruction, we're trying to just kind of hit surface level of everything. This is enough, okay? Don't freak yourselves out. Pause the screen if you need to, because I'm about to move on. All right, we've got one more example. We're going to identify troughs, crest troughs, wavelength, and amplitude. Pause it. See if you can do it by yourselves. I'm going to identify just one of each. This is a crest. This is a trough. An amplitude is from here, right here, to my midline, okay? A. And a wavelength, I'm going to go from here to here. Actually, if you were doing this problem like on a Google form, I would say pick 2 actual points and not just random pieces like I did. So for example, from F, ooh, that's a bummer. I didn't do a very good job on this, did I? From B to E is 1 full wavelength. There we go. All right, next up, a wave has a frequency of 16 hertz and a wavelength of 0.5 meters. What is the wave speed? Well, we are given the frequency of 16 hertz. We are given a lambda of 0.5 meters. We want the velocity, so V equals lambda times F. So that is 0.5 times 16. 0.5 times 16 is 8 meters per second. There we go. Make sure you include units on all of this when you are, especially when you are plugging in answers on any Google Forms. Waves are really interesting, so I want to be very clear. The frequency of a wave, the wavelength, the wave speed, and the amplitude of the wave, A, are all unique properties of that wave, okay? Depending on what kind of wave we're talking about, it means different things. So for example, the frequency in a light wave determines the color that we see. It's pretty cool. The amplitude in an earthquake will determine how much destruction that earthquake causes, and those are seismic waves. So these numbers will vary. They can be really big, they can be really small. Just note that like they will change, just like the velocity of a moving object will change depending on what object we've got, okay? So that's it for our lesson. Hopefully it was pretty clear and straightforward. I've got some practice problems up on Google Classroom. Feel free to work through them. If you feel really good about it and just want to go straight to the assessment, be my guest. That's it. Do great things, and I love you lots. I hope you have a great day. Bye.